So up to this point, we've been taking a look at vectors in terms of the magnitude of the vector as well as the angle measure, or if we want to describe it as direction. So magnitude and direction. What's the direction that our vector is going in and how strong is it? What's the magnitude of it? So what we want to do in this lesson, though, is we want to learn a different way to write vectors. And it's called component form. Okay, we want to write vectors in component form. Now, component form is really important to know because in the component form, the manipulation of vectors is a lot easier in most cases than taking a look at it in terms of a magnitude and a direction angle. So what we're going to do in this lesson is we're going to learn how to take a vector that is given to us, as this one right here is, in magnitude and direction form and convert it into component form. And then learn just some of the key pieces about that and then apply it to an example. So converting a vector into component form is nothing more than basic right triangle trigonometry. Okay, so we've got our vector here f, and the magnitude of vector f is 40, and the angle looks like 40 degrees above the horizontal. Okay, so here's what I'm going to do. I'm simply going to take this vector and I'm going to construct a right triangle with that vector as the hypotenuse. Now, based on the drawing over here, because this is horizontal, these two pieces are horizontal, I know that this is a 40-degree angle in here. Okay, and I know that the magnitude of my vector was 40, so the length of this side of the triangle is 40. Component form is nothing more than taking your vector and breaking it down into the horizontal and vertical parts. So to do that, basic right triangle trigonometry, let's see, this 40 right here is adjacent to this side down here. So that's cosine. So the cosine of 40 is equal to adjacent, we'll call this x, because it's along the x-axis, over hypotenuse, which is 40. So we've got x is equal to then 40 times the cosine of 40. Okay, so getting this out really quick, we can do 40 times the cosine of 40. And I get 30.64. Now I'm going to make sure really quick, I'm going to go to mode, and sure enough I am in degrees, so we're good there, so I can trust my answer. So 30.64. Oh, 30.64, not 3.64. Okay, so that's the x component. Well, what about the y component? What's the vertical component? Okay, to find the vertical component, right triangle trig again, except sine of 40 is opposite, which is that y over hypotenuse, which is the 40. So in this case, y equals 40 times the sine of 40. Okay. Go back to our calculator, 40 times the sine of 40 degrees, and I'm getting 25.71. Great, so these are the components. Now, really, this isn't any different than what we've done in previous lessons in looking at taking a vector and decomposing it into two separate magnitudes in two different directions. Except here we're specifically doing vertical and horizontal components of the vector. Okay? And so from here, here's the new part. What we're going to do is we're going to take these magnitudes that we found right here that are in the horizontal and vertical components of our vector, and here's how we're actually going to write down the vector. We're going to say that vector f, so f, and we've got the little half arrow on top to signify that it is a vector, is equal to, we're going to list the x part first, 30.64. Now everything, all the components in the horizontal, the x direction, gets a little I next to it with a vector symbol above it. And then plus our y component. That's 25.71. And everything in the vertical, the y direction, gets a j. So we would say that vector f is 30.64i plus 25.71j. The I indicates horizontal, the j indicates vertical. So this right here tells us how much is acting vertically and how much is acting horizontally, using the I and j as the identifiers for that. Right, so this right here is now our vector in component form. We've listed it not in terms of magnitude and direction angle, but we've listed it in terms of how much of it is acting horizontally and how much is acting vertically. Now, we can actually go backwards in this, which is kind of nice. Because essentially what we have here is we have a vector, and we know that the horizontal component is 30.64, and the vertical component here is 25.71. So if I were to go backwards and say I know my vertical and horizontal components, but I want to know my overall magnitude, well, it's nothing more, hopefully you see, than the Pythagorean theorem. A squared plus b squared equals c squared. Okay? X squared plus y squared equals the hypotenuse squared. To write it down in simpler form, we're going to say that the magnitude of f is equal to the square root, because this hypotenuse, you have to square root it on the other side. So the square root of the x component squared, so that's 30.64 squared, plus the y component squared, that's 25.71 squared. Okay, so I've got the square root of 30.64 squared plus 25.71 squared. I'm doing that, look what we end up with. It's, because of the rounding, it's not exactly 40, but that's 40. So the magnitude of f is 40, and that's what we had started with up here. So we can go backwards. We could also find the angle measure in here using, again, right triangle trigonometry. In this case, we could do something to the effect of tangent of theta is equal to opposite, which is 25.71, over adjacent, which is 30.64. So theta is the arctan, or the inverse tangent, 25.71 over 30.64. So verifying that, inverse tangent, 25.71 divided by 30.64. And sure enough, there's our 40-degree angle, 39.99999. So theta equals 40 degrees. So with basic right triangle trigonometry, we can actually go back and forth between magnitude direction angle form and component form. But here's why we want to be in component form. It has everything to do with how easy it is to add and manipulate vectors. Taking this vector we have here, actually I'm going to define two other vectors. I'm going to say that our vector f is equal to 14i plus 7j. 14i plus 7j is our vector f. I'm going to define another vector, let's call it vector h. And we're going to say vector h is 3i minus 10j. Okay? So looking at these graphically really quick, if I start at the middle here, my vector f, 14, let's go 5, 10, 15, so it goes over 14 horizontally and up 7. 5, 10, so 7's about here. Oh. Okay, 7's about right here. So this right here is my vector f based on its vertical and horizontal, so horizontal and vertical components. What about h? H goes over 3i, so that's horizontally 1, 2, 3. That's about right to here. but then negative 10. So I don't go up, I go down in the horizontal direction. 5, 10. And there's my vector h. Okay, so the goal is then we want to be able to add these vectors together. So f, and then if I brought h from here over to here, you know, there would be my h, so on and so forth. And what then would be the resultant of adding those together? Well, we could do that. It would take a little bit of time, but we've done that before. Here's the beauty of component form. In component form, adding vectors is really easy. Vector f plus vector h is nothing more than taking the I components and adding them together. So this would be 14 plus 3i plus, and then adding the j components together. That's 7 plus negative 11. And that's in the j direction. So f plus h is equal to, let's see, 14 plus 3 is, that's going to be a 17i. And then 7 plus negative 11 is negative 4. So that's actually be minus 4 in the j direction. Okay, there we go. It's as easy as that, adding vectors in component form. You simply add the i's together and you add the j's together, and here is our result. Does the result match the image? Looks like it does, because 5, 10, 15, 16, 17, I didn't draw perfect, my h here is a little off, and then down 4. Gets me pretty much exactly where I needed to be with adding those two vectors together. So in component form, add up the i's, add up the j's, and you've added the two vectors together. Okay? And what's nice is, what if you have 3 or 4 or 5 or 6 vectors? If you're dealing with magnitudes and direction angles, that can get insane. But when you're dealing with vectors in component form, it stays fairly simple, because if you have more than 2 vectors you're adding together, just add up all of the i's and add up all of the j's. So let's put this in context of an example problem. A sailplane. So a sailplane simply glides through the air. It has no propulsion system on it at all. There's no propeller, there's no engine, nothing. It's just gliding through the air. Okay? Now the forces acting on a sailplane, well, number one, there's weight. Right? It weighs something, so there's a force pulling down in the direction of gravity. There's also drag. As it flies through the air and cuts through the air is resisting its forward motion. So you notice this d vector drag is parallel to the direction, but in the opposite direction of where the sailplane is moving. And then lift. Lift is caused by the wings of the airplane. Okay, as it moves through the air, the wing profile provides lift. Now lift is always perpendicular to drag in most cases. Now, here's what the question is asking us. It says this: the force acting on the sailplane in figure 2.16 are its weight, and it says that W is equal to negative 600J. Notice it doesn't have any I. That's because it's completely vertical. There is no horizontal component. And then the drag D is negative 200I plus 100J. And the lift is L. And they don't give us any information about L, unfortunately, but that's what they're going to ask us in this first part. If the sum of the forces on the sailplane is 0, what are the components of L? Okay, there's a key phrase in here. If the sum of the forces on the sailplane is 0. In other words, in part A, it's saying that W plus D plus L is equal to 0. The sum is 0. Well, the question is there enough information in here for me to figure out what L is based on W and D? Okay, and there is, thankfully. Okay, so W, D, and L equals 0. What I'm going to do first is I'm going to look at the I components. So if w plus d plus l is equal to 0, all the I components better sum to 0. So what's the I component in w? Well, 0. Plus, what's the I component in d? Negative 200. Plus, what's the I component in L? Well, I don't know. We'll call it I sub L. And all that's supposed to equal 0. Well, this 0 here doesn't matter. If I add 200 to both sides, what does it say the I component in the L direction is? 200. So I now know the I component of my vector L. What about the J component? The vertical component. Well, again, all the J's should sum to 0. So the J component of W, negative 600, plus the J component of D, that's plus 100, plus the J component of L should equal 0. I don't know the J component of L, that's what I want to know. Well, negative 600 plus 100 is negative 500. Negative 500 plus J sub L is equal to 0. Adding 500 to both sides produces J sub L equals 500. So I now know that my vector L is equal to 200I plus 500J. So because I knew that they all should add up to 0, I was able to find that missing piece since I knew what the sum was supposed to be. So I now know my vector L. And there it is. Okay, so what are the components of L? 200I and 500J. Part B, though, says this. If the lift has the components determined in A, so we're using L that we just figured, and the drag increases by a factor of 2, what is the magnitude of the sum of the forces on the sailplane? Okay, so it's saying, let's add up W, D, and L, but what are we going to do to D? D increases by a factor of 2. So really what it's saying is, what is the magnitude of the sum of the forces on the sailplane if my drag doubles? So if my drag doubles, the equation that it's asking me to sum together is W plus 2D plus L. Okay? Well, we know that in order to sum these up, we simply add the components together. So the I's, this is going to equal, what are the I's? Well, W, the I component of W is 0, plus, now I can't forget the 2 in front of the D. The I component on D is normally negative 200, but we're doubling it, so that means it's negative 400. And then plus the I component in L. The I component in L is the 200. So this is the I component of the sum of W plus 2D plus L. And now the J component, okay, the J in W is negative 600 plus the J in D is 100, but again, we're doubling, so that's actually positive 200. Okay. Plus the J in L is 500, and that's what's acting in the J direction. So here, negative 400 plus 200, that is going to be a negative 200I, and then negative 600 plus 200 is negative 400 plus 500, that's going to be a plus 100J. So W plus twice drag, my drag increased by a factor of 2, plus my lift is equal to this vector. And it's asking for magnitude. How do we find the magnitude from component form? It's the Pythagorean theorem again. Okay? Simply put, it's the square root of the I component squared plus the J component squared. So this is equal to the square root of negative 200 squared plus 100 squared. And it looks like we're getting 225 223.6. 223.6, everything here is in pounds. So, before the drag increased, the sum of everything was 0, which essentially means the sailplane is floating around nicely. It's not falling or anything. It's just floating around. But the drag has increased, which means it's now got a sum of all the forces that's not 0, which means there's forces acting upon this sailplane. Okay. Great. So 223.6 pounds is the new sum when we double our drag back. So increase our drag by a factor of 2. So this gives you an idea of what component form of vectors are and how to add them and manipulate them, and even in this situation, how to take and multiply. This 2 right here simply gets multiplied into both the x and the y, or the I and the j component, in order to double it.